Hello and welcome back to our installments on thermodynamics 2. Today we will be talking about another improvement to the Rankine power cycle. Today's topic is regenerative heating. Before we get started, let's review the three Rankine cycle improvements that we've already talked about in our previous lecture. Specifically, we've talked about a method called superheating, reheating, and supercritical cycles. Superheating, as you remember, it consists of taking the saturated vapor that would typically come out of a boiler and heating it into the superheated steam state, and therefore increasing the overall high temperature reservoir temperature level, and therefore increasing the overall cycle efficiency as dictated by the Carnot analysis. The second method we've talked about was reheating, which consisted of splitting the turbine expansion stage into multiple stages, tapping the outlet of one turbine stage at an intermediate pressure, adding heat to it at that point, and then expanding the resulting reheated steam into a lower pressure turbine stage. The effect of this reheating is to again effectively increase the high temperature reservoir temperature, which has the net effect again of increasing the cycle efficiency. Lastly, let's look at supercritical cycles again. Remember that the supercritical point for steam is 22 megapascal and 374 degrees Celsius. And the point of the supercritical cycle is to bypass the saturation zone in the dome and to use a pump to bring us to a pressure higher than the critical point, so that there is no phase transition as the water heats up from the pump outlet to the turbine inlet, and no vapor bubbles effectively. All right, so today let's talk about the regenerative vapor power cycle. Another method of achieving the same thing, namely to increase the high temperature reservoir temperature for the purpose of increasing the cycle efficiency. So this is another method of increasing the high temperature reservoir temperature, as I said. Write that down. Very important. This is the means with which most power cycles efficiency gets increased. And the specifics of the method for doing that, first is to extract or bleed some fraction of the steam from an intermediate turbine stage. So in that respect, it's similar to what we were doing in the reheat method for increasing the Rankine cycle efficiency. However, instead of reheating the steam at that point, we are going to take that steam at this intermediate pressure, somewhere between the P high and P low, the high pressure isobar and the low pressure isobar of our cycle. And we're going to use it to preheat, since this intermediate pressure steam is still quite hot, certainly compared to the outlet of the condenser. So we're going to use it to preheat that saturated water coming out of the condenser, which is being pumped out of the condenser before it gets to the steam generator. Now there are two ways to achieve this that vary depending on the type of heat exchangers that we use. One is to use an open feed water system, which means we'll be using an open feed water heat exchanger, or to use a closed feed water system, a different type of heat exchanger. Let's start with the first one, the open feed water system. So open refers to the type of heat exchanger that we have. It's called an open heat exchanger, also called a direct contact heat exchanger, meaning that both streams come into direct contact with one another. This is different from the type of heat exchangers we've talked about before. In this particular case, the pump liquid stream and the turbine steam stream are both injected in the heat exchanger together, which means that their pressures must match. Otherwise, you wouldn't be able to mix them in that fashion, and that's a key feature of these open heat exchangers. So both the pump outlet and the turbine bleed pressure must match. As the pump outlet stream becomes warmer, the net effect of that, of course, is that the steam coming out of the turbine must also get cooler. And as it gets cooler, it condenses. And as it condenses, it generates more condensate or liquid water inside this open feed water system. And that total liquid water is what we're going to end up pumping back into the steam generator. Well, let's write that down. Now, of course, the benefit here is that as we pump this water, it is now at a higher temperature than it would have been had we not had this heat exchanger. And this increase in temperature and energy level of the water, if you will, is heat that we do not have to add to the water through the steam generator. And so therefore it's a saving on what we pay for, the heat added to the system. So let's put a diagram here to illustrate what the system looks like. The pro here, as I just said, is that we have higher temperature coming into the steam generator, and therefore a savings in heat being added, and necessarily, or as a result of that, a higher cycle efficiency. Without this heat exchanger, we would be at point A, but with it, we're at point 7. So the difference between T7 and A is the saving in energy that we don't have to add. The con, though, is that we need these two pumps added to the system. Here they are, and here they are on TS diagram. We have to do this because we have to pump the condensate out of the heat exchanger to the high pressure reservoir in the system. So we have 3 different pressures now in this system. Note that we're also losing some power coming out of the low pressure turbine since we don't have the same mass flow rate through it, but that's more than offset by the savings in heat added. The second system that we have is called a closed feed water heat exchanger system. And the closed feed water system, as the name suggests, both streams do not mix as they did in the open one. Typically, this is a shell and tube heat exchanger arrangement, like we've talked about before, so that the pressures of both streams can now be different. So benefit there is that we can make do with a single pump. That pump is going to push the condensate straight through to the steam generator, since it doesn't have to interact with the steam coming out of the turbine directly. The con, however, is that we are going to have a lot of condensate coming out. As we remove the heat from the steam, we're going to generate some condensate water, which will then have to be throttled back down to the condenser of the system. And that throttling process, because it's at a lower pressure than the intermediate pressure that the turbine steam / condensate is at, that throttling process produces large irreversibilities in the system, as you can see on the TS diagram there, between 7 and 8. And that large irreversibilities is an increase in entropy in our system. One of the net effect of that is that the net temperature, the temperature of the feed water that's delivered to the steam generator, is going to be lower than the saturated liquid temperature 7 that you have in the case of the open feed water system. But nevertheless, in modern power plants, a combination of both open and closed feed water heaters are used to try and optimize the efficiency of the power plant while maintaining good economics in the process, because obviously these systems involve increased complexities as we move along. Next, we're going to do some more detailed analysis of the open feed water system here. Okay, so let's go back to the open feed water system and do an analysis on the open feed water heater as our control volume here. So the purpose of this analysis here is to look at the properties in and around the open feed water system to try and figure out a relationship for the mass fraction that's actually tapped out of the intermediate pressure turbine as a function of those properties. So to figure out that mass fraction, the mass fraction Y, that's bled out of the turbine, we're going to do specifically a mass and energy balance on a control volume of that heat exchanger, the open feed water heater. So let's get started with that. So here's the sketch of the cycle from before. I'm going to try and keep that for the rest of the analysis here as I draw a control volume representing the heat exchanger with the 2 inlets and the 1 outlet. We have 1 inlet from the high pressure turbine, that's state 2. We have 1 inlet from the low pressure pump, that's state, let's see, 5 on our diagram. That's from the low pressure pump, right? So that would be water being pumped from the condenser. And we have 1 outlet, which is the condensate from the open feed water heater that goes to the high pressure pump and then to the steam generator. So at each of those points we have mass flow rates and enthalpies as stated here. So first let's apply the conservation of mass to this, and for the sake of this problem here I'm going to go back to the very general Reynolds transport theorem form of conservation of mass. I think it's a good place to use it as an exercise because it's kind of an easy example, and you can see how this intimidating form can actually work out to be something a lot simpler than it first meets the eye. This, first of all, that transient term goes away as I've just shown here, and the convective term, which takes into account what comes in and out of the control volume, in this particular case we have 2 inlets and 1 outlet, readily boils down to the 2 masses in minus the mass 1 out goes to 0. So M2 plus M5 has got to be equal to M6 is what we're saying here. Now I could be a little bit more rigorous here to look at the velocity profile and make some assumptions, but I'll save that for the energy equation that we're going to do next. Okay, so that box equation here relates all 3 mass flow rates that we've got into our control volume, assuming steady state. Now let's do an analysis on the high pressure turbine now, from the high pressure side 1 to the intermediate pressure side 2 that's being bled to the heat exchanger, just so that we can relate the overall mass of our system, which we've been calling m.1, to these 3 masses that we've got here on the box equation in yellow above. So right off the bat, we see that since there's only 1 in, 1 out, out of the open feed water heater and the high pressure turbine, that M6 must be the same as M1, and that's what we are noting here. And the rest, the amount of mass flow to the low pressure turbine is given to us as 1 minus Y, where Y is the mass fraction that's being bled from the inlet flow, which is m.1. So voila, we have a set of basically 3 equations that all relate the 3 variables that we had in the yellow box equation above all to m.1. It's going to make our life simpler down the line later. Okay, enough for the conservation of mass. Let's move on to conservation of energy. Again, we're going to start with the raw general form of Reynolds transport theorem, and we're going to try and be a little bit more systematic on this one. and state our assumptions as fully as we can as we go through it, because I want to use this energy equation exercise as an exercise of applying the Reynolds transport theorem to a problem. So this is the energy equation in Reynolds transport theorem form. First is the transient term, which we're going to ditch in a minute, but let's write it down. Remember, E is the specific stored energy of the system. That's going to be made up of internal energy, kinetic energy, and potential energy. Let me move this out of the way here. But the kinetic energy and potential energy are going to be neglected. We'll do that in a second. Okay. So first, let's remove that heat in term and that work out term, because we have made explicitly the assumption that the heat exchanger is adiabatic. There is no heat loss to the surrounding. The transient term goes away because we're at steady state as usual. So again, we have just a convective term with 2 inlets and 2 outlets. Oh, and I should have said that the properties are uniform here as well. We'll write that down later. So I'm expanding here the specific stored energy term in terms of the various energies that the stored energy is made out of, and immediately removing the kinetic energy and potential energy, because those don't play a significant role in these types of thermal systems. However, we do have the flow work term, the P over rho term in here, which gets added up to the internal energy to give us the enthalpy. So that's where the enthalpy comes into. So now is where this uniform flow and uniform flow property assumption becomes important, because we are going to be able to remove the rho and the h and the u's out of this integral, and we're going to have rather trivial integral, which is a really nice form of the energy equation. But it's good to see that it comes from this general form that we took so long to derive and to understand. So for this particular problem, for this control volume, with the assumptions that we made, we only have 3 terms. 2 are the inlets to our system, and here let's derive really the relationship between velocities and the normal to the surface at an inlet. So we see that the velocity and the outward normal vector are in opposite directions, which means that they are at 180 degrees to each other, right? And since the dot product of the 2 vectors is the magnitude of each vector times the cosine of the angle between them, that cosine of 180 is going to throw in a -1 term for all the inlets, and similarly a +1 term for the outlets, because there the velocities and the unit normals are aligned and the angle between them is 0. So dealing with the inlets first, I've removed all the properties to the outside of the integral. So rho hu are out, and I'm just integrating over a, so that brings out a now, easy. And rho ua is just the mass flow rate, so m dot. So for my inlets, I've got minus m dot h, and for my outlets, I've got plus m dot h's. Putting those 3 terms together here, I've got the minus m dot h at the inlets, plus the m dot h at the outlets. All that's got to be equal to 0. So putting my 2 inlets on one side and my 1 outlet on the other, I've just got positive terms here. And now is when we fold that in back with our conservation of mass analysis from above. And it's real convenient that we simplified these M2, M5, and M6 in terms of a single variable M.1, which is our total mass flow rate, because now we can substitute that back into this. So let's label these things. The 3 mass flow equations, let's call them equations 1. And our 1 energy equation, let's call that equation 2. And so we're going to substitute these 3 equations 1 into that 1 equation 2 in terms of just m.1 to keep things simple. So m.2 is simply the mass fraction rate y times m.1. m.5 is 1 minus y times m.1. And lastly, m.6 is simply m.1. So lo and behold, all these m.1s cancel, and we're left with a single expression in terms of y and h's, which is the goal of this exercise, right? Doing a little algebra here to isolate the y, and voila, we have the mass flow rate that neatly comes out as a function of the enthalpies of the inlet and outlet flows at the end of the day. And this is how we're going to figure out how much mass was actually pulled out of the turbine here. So the mass fraction of steam that comes out of the turbine, that's Y in their little diagram there. That is simply a function of the enthalpies of the system